All right, so here we go. We're talking about this test right here. Make sure you're looking at the right version because there's several versions. There's 4 or 5 different versions of this. I'm going to take this from the most basic level. I'm not trying to insult you. I'm just trying to go back. You can try to think of this as a review if you want to, okay? So this equation is asking you the most basic question. Write the balanced equation between hydrogen. We're going to combine hydrogen and oxygen to produce water, okay? So the first mistake that was made was not writing hydrogen and oxygen as diatomic, okay? They have to be written as diatomic. They exist only as diatomic elements, okay? And so when they're in their pure state, they're always diatomic. Now that puts the reaction out of balance. You got 2 oxygens over here. Excuse me. You have 2 oxygens here and 1 here, so you have to balance the equation, okay? Now the hydrogens are out of balance, boom, okay? And what's going on, if you're interested, is you have these hydrogen atoms. When they're pure, they have 1 electron, okay? They can't exist. An unpaired electron, Mr. Gradle, excuse me, okay? Do me the favor of listening, okay? The unshared electron is unstable, okay? It's called a free radical. So when 2 hydrogens, when there's nothing but hydrogens in the vicinity, they share these 2 electrons. They share these 2 electrons, Mr. Bebe. They form a covalent bond, and that's why we have diatomic hydrogen. The oxygen, same, but different. The oxygen, as you remember, has these 2 shared pairs up here and the 2 unshared electrons here. Very unstable. Very unstable. Okay? And so what happens is, if you don't mind me turning this thing upside down, is I'll turn this oxygen upside down and put its paired electrons up here, and what happens is the oxygen shares 2 pairs. So you have that oxygen with the double bond, okay? And that's what's happening. And yes, that's a review. That's a review of Lewis dot structures, okay? That's a review of electronegativity and molecular geometry and so on and so forth, okay? All of those things you're going to see on the test, all right? So there's the balanced chemical equation right there. What type of reaction? I think the best categorization would be synthesis. Maybe some books will call it combination. And I had some people say combustion, and I'm not sure I would rule out combustion, okay? It fits the classic definition. Somebody correct me, Miss Farnham. The classic definition of creating oxides, okay? Adding oxygen to create oxides, okay? So I didn't rule it out. I don't think I marked anybody's wrong for synthesis, combination, or combustion, okay? If I did, we'll correct it, okay? So that's question 1. Question 2 says, how many moles of water can be produced from 6 moles of oxygen? Well, again, we got okay, so we got 6 moles of oxygen, yes. When you strike a match to pure hydrogen, what happens? Think Hindenburg. Think rocket going to moon with lots of white plumes below it coming out the tail end of it. That's water. That's water vapor being produced. Hugely reactive, yeah. Yes. 6 moles of oxygen. We want to know how many moles of water. So we're going to put moles of water over here. For those of you that haven't picked up on this yet, if you can identify what you're given and what you're asked for, which should be easy for you here, how many moles of water, put that on the right. What you're given, 6 moles of oxygen, put that on the left. And then your conversion factor looks just like this. The answer unit's in the numerator, the given unit's in the denominator. So you have moles of water here, you have moles of oxygen here. And where do you get this ratio? The ratio comes from the balanced chemical equation, okay? This is a 2 moles of water to an understood 1 mole of oxygen, okay? So the moles of oxygen cancel, and we end up with 12. That was the crux of the matter in question number 2. And it's a very simple thing, Miss Spickle, but what I'm asking you to do is demonstrate that you understand this, okay? because we're going to be working problems here where these are like 4 or 5 significant digit figures and so on and so forth, and it won't be quite so simple. But the crux of the matter is this: simple. Okay? Now, we had a couple of people just gave me the 12. Put 12 in the answer box. That is not what I'm looking for. I'm looking for a demonstration that you understand how to use a balanced chemical equation. The previous question was a demonstration that you know how to write a balanced chemical equation. Okay? So it's this is very, very prescriptive. I'm not trying to be a nitpicker, but I mean, this is the way it is. Okay? Question number 3 says, for the same reaction, the hydrogen and the oxygen producing the water, for the same reaction, how many grams of water were produced from 6 moles of hydrogen? Now you notice we changed reactants as our given units, which changed the coefficient. Okay? Which changed the coefficient. So here I'm asking you, do you understand the steps you're going to have to go through here? Okay? And what you're going to have to do is start with your given unit, which is 6 moles of hydrogen. And what we want to eventually end up with is grams of water. Now, this one is much more difficult than the previous question because it requires you to know on site that you're going to have to go from moles of hydrogen to what? Moles of water. And then from moles of water to grams of water. Okay? Much more difficult. In the other question, it's almost completely given to you. Here, you have to know this. You have to know that you can't convert. You can't convert from one substance to a different substance in any unit other than moles. Okay? So, once you get it to this stage, it's very simple again. You're going to have moles of water here, moles of hydrogen here, and what's the ratio? 2 to 2. So this will give you 6 moles of water. And now here, again, the answer unit is in the numerator, given unit is in the denominator, and 1 mole of water. People are still trying to use these coefficients in here when they calculate this mass. No, this is per mole. You could do it if you do it correctly. You could put 47 moles of water here if you want to. You just make sure you get 47, the mass of 47 moles of water. But why do that? Put 1 mole in if you can, okay? Everybody should know the mass of water now is 18.02 grams. Any questions about 1802, where we got that? Okay, so we multiply that out, and what do we come up with? 60 and 48.12, so it comes out to what, 108.12. We're given 3 significant figures here, so we have to reduce this to 3 significant figures. Everybody understand that? Any questions about that? Okay. The next question, if we come back here and look at it, question number 4 says we got 5 grams of solid silver is added to a solution of excess copper 2 nitrate. Now immediately, Miss Farnham, when you say or you read that we're going to add silver to copper 2 nitrate or virtually any other soluble salt, you should be thinking already no reaction, okay? Silver is one of the least reactive metals on the board, okay? But even if you didn't know that, when you look at this potential single displacement reaction, you have to think activity series, okay? The activity series is page 286, okay? And that's where you can read all about the activity series. Some metals are more reactive than others. Halogens, you'll see, some are more reactive than others. You have to keep that in mind, okay? This is something we learned, weeks ago, and now you have to use it, okay? So we got silver. We're going to take silver, and we're going to add solid silver to copper 2 nitrate. The equation for copper 2 nitrate is what? That 2 is a 2 plus. Okay? You're not allowed to write it. People are still trying to write it. I'd rather have you write it and know it than not. But you're not allowed to write it. The nitrate, I got all kinds of innovative formulas for nitrate, but nitrate is NO3 with a 1 negative, therefore you need 2 of them. Okay? You have more than one polyatomic ion, so you surround it with parentheses, and the subscript tells you how many ions you have there. Okay? A lot of people are violating that rule in writing these formulas. Okay? Ms. Pickle, you got that? You do not use parentheses unless you have more than one polyatomic ion. You do not put parentheses around a monatomic ion. Okay? And so here we had some people that would rewrite, understood this was a no reaction, but they would rewrite the reactants. Don't do that. Write, be explicit, no reaction. Okay? Yes? Okay. So that's question number 4. Any questions about that? All right. Question number 5 says, now we're going to reverse this situation and we're going to add copper to silver nitrate. Now, you look at the activity series, and for the same reason that the silver could not displace the copper does displace the silver because it's higher on the activity series. Okay? Yes. So let's see if we have this one written out here. Yep. Okay. So here we have copper. We're going to add solid copper, and it has no charge on it. It's got a 0 charge. It's got all its electrons, and we're going to combine this with silver nitrate. Now here, this is a little bit, I don't know. You just need to know. Silver is 1 plus. Silver, zinc, and cadmium are a few of the ones that you need to know. Now here, instead of no reaction, we do have a reaction. Okay, the copper is going to displace the silver, and I would accept it either way. If you wrote it as copper 1 nitrate, it would just be, that'd be the easiest. It'd be copper nitrate. Okay, this is aqueous solution, and you would have solid silver. That's a G. You would have solid silver precipitate out. Be a nice situation if you could get enough of it, collect the silver, and get rich, right? Okay. So if you wrote this as copper 2 nitrate, and I looked it up, there is a form of both. I think the copper 2 nitrate is more common, but there is a form of both. But if you left it as copper 1, it would be here. If you did copper 2, you'd put your parentheses around it again. Your 2 would be here, so you'd have to have 2 nitrates over there, and that would force 2 silvers over there. Okay? So we'll calculate it with the 5 grams here, okay? It says predict the results and write the balanced chemical equation, okay? So it's not asking you to calculate anything here, okay? Now the next question, any questions about that? Activity series again. Copper's higher than silver on the activity series. It's also higher than silver on the periodic table. You have to bring yourself to remember that you need to think activity series, okay? Now here, another situation, and this one, you know, I sort of feel guilty about asking you this because you don't see these very often, but it is a typical SOL question, okay? You're going to add bromine to potassium chloride, okay? And what's going to happen? You look at the activity series, happens to be the same order as on the periodic table. Bromine's below chlorine. There's not going to be a reaction. Okay? Again, activity series, page 286. And I keep giving you the page number, Mr. Green and Miss Hinton, because I'm hoping you'll go to that page and look at it and maybe read a little bit about it. And you know what happens when you do that is there's a much greater chance you might remember it. If you just hear me talk about page 286, the odds of you remembering it is much less. Got it? Okie dokie. All right, next question. Number 7. Where are we here? Number 7 says, how many grams of the resulting something will be produced? Well, there won't be any reduced if there's no reaction, right? So we go to number 8, all right? Number 8 says, the answer is here, we're going to say no reaction equals no resulting salt. Everybody understands the salt is the ionic compound, right? Everybody got me here? Right? All right, so we look at question number 8, okay? And now chlorine, we're going to add chlorine to potassium bromide, and now we have a horse of a different color. Chlorine is higher on the activity series than bromine, so what happens, Miss Clark? We're going to call this aqueous. This is a salt. This is a gas, okay? Another diatomic element. So what's going to happen here? Chlorine's more reactive than bromine. They're both one negative ion, so we're going to end up with potassium chloride and bromine. Bromine's a diatomic element. So this throws our reaction out of balance, so we got to balance it by how? This gives us the 2 bromines with a 2 here. This gives us a 2 chlorine with the 2 here, and we got 2 potassiums balance themselves, right? Okay? Any questions? Miss Hinton, you got that? Okay. Now, grams of resulting salt. Let me put this up again real quick. What is the resulting salt? The resulting salt, somebody? What is it? What is the resulting salt in this case? Potassium chloride, okay? Now, 175 grams of each reactant. So what do we have here? We have a limiting reactant question, okay? Now, this, again, is something you have to bring to the table. You have to look at this and realize that this is a limiting reactant question. Every chemical every question about a balanced chemical equation or chemical reaction is potentially a limiting reactant question. Most of them tell you that, you know, the other product, the other reactant is in excess and so on and so forth. This one deliberately says you got the same quantity of each reactant. So you have to calculate both, okay? 175 grams of chlorine and 175 grams of potassium bromide, okay? Now, calculate that out, and we know that we're going to have to go to do any kind of conversions through this balanced chemical equation. We're going to have to go through moles. So the first thing we do is convert to moles, okay? 1 mole of chlorine has a mass of 70.90 grams. So we end up with how many moles there? 1 mole of potassium bromide has a mass of what? 166? 119. What's 166 something? 119, and that's not being lazy. It's 119.00, right? So we didn't lose any significant figures. Correct? So, what is the number of moles here? Okay, so for the chlorine we have 2.683, right? Huh? 2.4683 moles of chlorine, and we have 1.4706 moles of potassium bromide. Okay? Now, does everybody understand how this works? The grams cancel. Grams of potassium bromide cancel, okay? So what we do then is all we're doing is dividing the 119 into the 175. Right? Ms. Clark, got that? Here we're dividing the 70.9 into the 175, okay? That gives us moles of chlorine and moles of bromine. Now, because this thing is asking you for the grams, eventually it's asking you for the grams of the resulting salt. We know the resulting salt is potassium chloride. A shortcut then is to convert directly to potassium chloride here, okay? So we can't go straight to grams of potassium chloride. We got to go to moles of potassium chloride. And again, this is a question of you understanding that, okay? So if we do that in both cases, what we're going to do is we're going to kill two birds with one stone, okay? We're going to determine what the limiting reactant is, and we're going to halfway complete the question. Everybody understand that? So we want to convert this to potassium chloride. I'm sorry, this is a 2 to 1, right, mole of chlorine. This is a 2 to 2 moles of potassium bromide, okay? So we end up over here with this state. Let's say we end up over here with 4.9365, and I'm 4.9365 moles of potassium chloride. Here, 2 over 2 is the same as 1, so this doesn't change the quantity of this, 1.4706 moles of potassium chloride here. So now we know that this is the limiting reactant. That is the limiting reactant, okay? The one that produces the least product. In other words, it limits the reaction. Okay, so that's the limiting reactant, and the importance there is that's the one we're going to use to calculate the final answer. Okay, so we just go 1.4706 moles of potassium chloride, and then we're going to go, we want to know grams of potassium chloride. So just like we've been doing all along, grams of potassium chloride goes here. And this unit is here, which is moles of potassium chloride here. And this is 1 mole of potassium chloride, has a mass of, I believe it's 74.55 grams. Yes? And we calculate this out, and we come out to 109, I believe 109.633. And we're only allowed how many significant figures? 5, okay? So we're going to go to 109.63, okay? And that's the correct answer. Questions about that? Now that's one of the more difficult ones. I mean, it's difficult in the fact that it requires more steps. But the real question is here, do you understand, do you recognize the things that you have to do? Do you recognize the steps that you have to take to answer this question? Okay. Okay, so that's number 9. Number 10 says we have 16.3 grams of metallic magnesium. Okay, reacts with 12.5 grams of steam. Again, this is another limiting reactant. Okay, predict the results and write the balanced equation. Okay, so what we're going to do is we're gonna write the equation, balance the equation first, and then find the limiting reactant. In fact, it asks you for the limiting reactant here, which if you didn't pick that up here, that should jog your memory up here on the previous question. And question number 10 says it's another, look here, we got grams of reactant, and we got grams of reactant. And you can bet that that's a limiting reactant question, right? The first thing says write the formula and balance the equation, so on and so forth, and then we'll go to the limiting reactant part, okay? So let's see where we are here. Okay, so predict the results and write the balanced chemical equation. All right, so we look at magnesium, and you could say to yourself, whoa, is magnesium going to be able to replace it, going to be able to pull the hydrogen out of here in steam? So you go to you could go to page 286, the activity series, and you'd find out it would tell you. But you also got to understand here that this thing is telling you we produced magnesium hydroxide and hydrogen gas. So this equation is telling you that it goes forward, okay? So when we say predict the results, that's really not a true prediction because you're told in here what's going to happen, right? So we're going to take metallic magnesium, and what that means is the magnesium is solid. Got an oxidation state of what? What's the oxidation state on the magnesium? 0, if it's solid, right? 0. So what's going to happen is the magnesium is going to pull one of these hydrogens off of here, right? And then the magnesium will hook up with the hydroxide, which is left. And what's the charge on the magnesium? It's always 2 plus. Hydroxide is OH. What's the charge on the hydroxide? 1 negative, so you need 2 of them. Okay? Now, a lot of mistakes, don't use these parentheses on anything but polyatomic ions, and only when you have more than one. Okay? Don't put the parentheses around monatomic ions. All right? So now you can see already we've thrown this thing out of balance because we got 2 oxygens over here. Okay? And so here we're going to produce hydrogen gas. All right? And it's going to bubble away. Okay? And so you see that we've got over here, we've got 4 hydrogens and 2 oxygens. That's not going to work the way it is. So we need a 2 here. Okay? So that's balanced. Yes? Everybody agree? Okay. Now, limiting reactant. What is the limiting reactant? What are we going to do? It's just like the one I just explained to you. Well, somebody tell me. Well, yeah, but I mean after that, what are the steps we got to go to? Huh? We're going to take grams of metallic magnesium, grams of magnesium to moles of magnesium, grams of water to moles of water, okay? And then what we're going to do here is we're going to eventually calculate how much extra we have, okay? So we take 16.31. Now you're working along with me, I hope. 16.31 grams of magnesium. And we're going to convert that to moles of magnesium. And we're going to take what do we have here? 12.15 grams of water, steam, okay? And we're going to convert these to moles, okay? Well, 1 mole, well, let me do it this way. We're going to moles of magnesium, and we're going to moles of water, okay? And we know that when we're doing any conversion, that this unit we're going to is going to be in the numerator. Both cases. Everybody see that, Miss Hughes? You got that? Yeah. Moles of water. And where are we going to get this relationship? The unit we're coming from is going to be in the denominator. So this is grams of magnesium, and this is grams of water. So where are we going to get these figures here? Periodic table, right? Magnesium has a mass of 24.31. and water has a mass of 18.02. And both of them, you can see we're going to come out to about 2/3 of a mole, right? Less than a mole. What does it come out to? I think we come out to 0.6709, right? 0.6709 moles of magnesium here, and 0.6743. Is that correct? Moles of water here, okay? So now what are we going to do? What's next? We haven't told ourselves anything yet. We just converted units. So now we got to go to the balanced chemical equation, okay? Now we got to go to the balanced chemical equation, and I kind of cheated and looked ahead, and I see that the next question is going to ask me about hydrogen, so I'm going to calculate the amount of hydrogen produced, because I know eventually I'm going to have to do that anyway, right? And the one that produces the least amount of hydrogen is the limiting reactant, right? So in both cases here, I'm going to do the same thing. I'm going to go 2 moles of hydrogen. Moles of hydrogen, okay? So this is moles of hydrogen here. And you wonder why you have to write this twice. You have to write this twice so you can show anyone that's looking at your work. At this stage, it'll only be me. But someday it might be, you might be doing something for a living, right? That someone's got to follow. So you have to make your work clear and precise and organized and systematic, okay? So moles of hydrogen to moles of in this case magnesium, in this case water. Well, 1 mole of hydrogen in both cases to how many moles of magnesium? Huh? 1 mole of magnesium. Everybody knows where that comes from, Miss Hughes? The understood 1 is here, right? And the understood 1 is here, right? Okay. So here it's a 1-to-1 ratio. Now here, it's moles of hydrogen to moles of water. What's the relationship? This 2, okay? This 2 right here. I'm going to do this in, whoops, try to do this in red. Okay, so this is 2. That's the key. That's the story, right? So this comes out to, this stays the same, 0.6709. This comes out to 0.3371, right? Everybody agree with those figures, 3371? Now what have we got here? At this stage, we know this is the limiting reactant. Right? Everybody got that? You understand that, Mr. Moreland? Okay? That's the way that's done, okay? Now the next part of the question says, how many moles of excess reactant will be? Well, if this is the limiting reactant, let me make that clear, L. If this is the limiting reactant, then this must be the excess, right? Well, this question just says how much excess, right? Okay, so how much of this do we need? How much of this well, the excess is over here. I'm sorry, the excess is the magnesium. Okay, so we take our quantity of limiting reactant, okay, which is 0.6743 moles of water, and we're going to convert that to moles of magnesium, right? So we're going to see how many moles of magnesium we're going to need to react with all of this. I'm sorry, this is water. It's sloppy. Sorry. This is water. 2 moles of water. All right. But does everybody follow what we're doing here, Ms. Wong? Do you understand what we're doing here? Yeah. We're trying to figure out, we're saying how many moles of magnesium are we going to use now that we've determined the amount of water, that water is a limiting reactant. How many moles of magnesium are we going to use when we use up all this water? Okay, so we go back to this chemical, this equation, the chemical equation in the molar ratio, and so we cut this in half, and what does it come out to? It should be about 0.3371, right? Moles of magnesium. Now what is that? That's how much we need, right? Everybody got me? I still, to this day, when I work these problems, I write that down. That's how much magnesium we need. How much do we have? That's how much we have. Everybody with me? Who's not with me? Who is with me? Okay, so we're going to write this down. We're going to say we got 0.6. Trouble changing these colors. I got 0.6709 moles of magnesium. That's how much we have. 0.3371 moles of magnesium. That's how much we need. Now that also happens to be the number of moles of hydrogen we're going to produce, right? Because this is a 1 to 1 ratio, but we did it the more logical way. So what are we going to do? Subtract the difference, and what do we get? I think we come up with 1 from 9 is 8. What is that? That's going to be 3, right? 6, and that's going to be 3, and that's going to be 3. So that's how much excess. That's the excess amount. Okay? Now, normally the only place you're going to be calculating this is on a test type thing, okay? Like how much reactant, how much of this reactant or that reactant would be left over and whatnot. And all it is a check to see if you understand this whole concept of limiting reactant. But generally, that's the only reason for doing that, okay? Any questions about that? By the time I finish putting all these marks on, it looks kind of sloppy, but I mean, I hope you followed through with that, followed through that, okay? Okay, so let's go to question number 13. I think it still relates to this question. Number 13 says, let's see, that's 12, how many moles of excess? And number 13 says, what is the theoretical yield of hydrogen gas? Okay, does everybody understand theoretical yield? Okay. Theoretical yield is the amount that could be produced, let me go back, from the limiting reactant. In other words, right there, 0.3371 moles of hydrogen gas is the theoretical yield. Does everybody understand that? However, it asks you in grams, right? The theoretical yield is the quantity produced if all of the limiting reactant goes to product. How's that? If all of the limiting reactant reacts, that's the theoretical yield. Got it, Ms. Hughes? Okay, so then that makes that easy. Okay, what's the theoretical yield? What do we have? 0.3337. Is that what we had? 33. Yeah, 0.337. So I'm going to add the other significant figure there. 0.3371 moles of hydrogen. In fact, it didn't ask for grams, did it? But I'm going to take it to grams, okay? And we have 2.02 grams of hydrogen per mole of hydrogen. And so that gives us what? 6.810, or 0.6810 grams of hydrogen. Okay? That is the theoretical yield. That is the theoretical yield. Now, where we're going here in the chapter coming up, it might ask us for the volume. Let's say, Mr. Curtis, this is at STP. Okay? So we say at STP, what's the volume? You would multiply this by 22.4 liters per mole, right? Be about 8 liters. Okay, everybody got that? Now, another question, Mr. Roussel, is another way to look at this is what is theoretical yield? Well, the theoretical yield equals what? In terms of our equation that we're going to come up with shortly. The percent yield equals the actual over the theoretical. So what does the theoretical equal? It's the actual yield over the percent, right? Okay. But anyway, here we go. So we're looking at that. Here we say, okay, so we got a percent yield of 93.21. What mass of hydrogen gas is produced? Well, we know that percent yield equals what? Actual yield over theoretical. So, what do we ask for here? I should have maybe put this here. What is actually produced? This is your actual yield. Okay? So the actual yield equals what? According to this equation. Say it again. That's right. Equals the percent yield multiplied by theoretical yield. Okay? Now, when you look at it like that, it's pretty simple, isn't it? Huh? So, therefore, the actual yield then, if you, first of all, the first key to this question is realizing that it's asking you for actual yield, okay? The percent yield's given to you, okay? The percent yield is point, and of course you realize you're going to divide by 100, 0.9321. There are no units there. And you're going to multiply that by this percent yield that you calculated up here, 0.6810 grams of hydrogen. And you do that calculation, what do you come up with? 0.6348 grams of hydrogen. Okay? Now, there was only a few people that got that right. But you can see now, hopefully, that that's not a difficult question, right? I mean, if you realize you're looking for the actual yield, and if you think about it in these terms, it's not that hard a question. The trick is, how in the world are you going to remember that? I don't know. I think the only way you're going to remember is practice. You're going to have to work, multiple theoretical actual yield questions, and then you'll burn it into your brain. You'll remember it. When I was in college, they called that churning and burning. They're trying to cut that out of chemistry now, it looks like to me. But it takes practice. I have to work a lot of them to remember how to do them. Okay? But anyway, so we get to chapter 15. We've already answered that question. Mathematical relationship between percent yield, actual yield, and theoretical yield. Well, the way I write it is in terms of the percent yield. The actual yield over the theoretical times 100 equals what? The percent yield. And you can turn that around any way you want to turn it around, but generally the most common question is, what is the percent yield of this reaction, or so on. It says if you calculate, if you produce so many grams of this product, what is the percent yield? That's usually the question. More difficult question is like this one right here. That's why I wanted to give it to you, is they give you the percent and ask you for the actual. Okay? And if you look at it in terms of this mathematical relationship, it's really not difficult. It's no more difficult than the other one. Okay? Any questions about that? Good. Okay? So that's straight from me to you.